Hello, people of Computer Dove. I have officially become the vice captain of Elzahraa American School, and since I have such high authority now, my messages they need to be encrypted, and they need to be encrypted well, so no spies can listen in to my secret conversations. Which is why today I have Mohamed Zarkuni, the perfect guy to ask questions about encryption. Hello, Mohammed.
Hello, Adam. Thank you so much for inviting me today. For those of you who do not know, I am an encryption master. I'm an expert on this topic. I am very well versed in all kinds of encryption. As a matter of fact, I was closing on closing a PhD, but unfortunately didn't. So let's move into our secret whiteboard here. It's a pretty cool whiteboard, and let's move into it. So the problem is when I'm going to call this myself, and I'm going to call this Adam, and we would like to send, or Adam would like to send very secretive messages to myself. And the problem is there's people here who could listen to these messages, whether that is actual like conversation or if it's over the internet. And that's a big problem because if someone listened, they could report, depending on what kind of message it is, it could be very harmful to Adam and myself if these messages are discovered. And that's why you need the messages encrypted. Am I right, Adam?
You are very correct.
Okay, so how do we encrypt these messages in a way that is understandable to myself, but if someone from the middle takes these messages, understands nothing about what these messages contain? And a very easy way to do this is to actually shift the letters. So let's say our secret message is ABC. So we're going to shift the letters forward. And so I'm going to say B, C, D. You're going to send that message by shifting all the letters ahead by one. And I myself, I'm going to understand that what I need to do is move them back so that I get my original secret message of ABC. However, say this person is called Eve because they're spying. They're going to see this message that doesn't make sense, right?
They're going to try to understand it.
They will. But because it's shifted by one or by two or by three letters, it doesn't make any sense. It's garbled, okay? And so what happens is it goes to myself, okay, from Adam to me. I understand that you shifted the letters by one, so I reshift them. But there's a problem with this. There's actually many problems with this kind of thinking. So the first problem is Mohammed has to meet with Adam, okay? So basically they call this Bob and Alice in the world of computer science, but the two parties have to meet in order to find the key. So what is the key? The key is what we're gonna do to resolve our messages. So in this specific case of shifting the letters from A to B, B to C, C to D, the key was just +1. And so this key had to be shared with Alice and Bob very securely, okay? We had to physically meet, okay? But what if we can't physically meet? This algorithm or this way is useless, right?
Yes.
So basically we have to meet. But let's say I do something really stupid here, okay? Let's say Alice does something pretty bad, is she sends the message and says the key is +1, okay? So she sends the message, it's gonna be like B, C, D, and she says the key is +1 in the same message. So what's gonna happen is Eve, who's standing in the middle, is gonna understand that key is +1. So she's able to decrypt the message just like Bob does. So that's why the key is secret. And this is called private key encryption. And it only works if there's a chance that Bob and Alice or Muhammad and Adam actually physically meet in the real world. But that's not always viable. Now, is it?
It is not. Sometimes we cannot even meet. We're too far.
Yes. Like, according to my calculations, there are like allegations of the new vice captain being involved with the KGB, and so these problems or these things or these entities cannot physically meet one another, right? So in this case, private key encryption doesn't work. So what do we do? That's a very good problem. Okay, now we move on to a very interesting concept. But before we move on to it, basically, it really helps a lot if we see how messages are transmitted over a network or over a computer. So when you send the message of ABC, it's sent in something called the ASCII format, ASCII format. And so what that does, it's a very easy thing. It maps each letter ever into a single number, one-to-one function. So it says A is 97, and you could look these up. If you say what's the ASCII code for the small letter A, you get 97, B is 98, C is 99. So when you send the message of ABC over the computer, you only send the bytes 97, 98, 99. And the receiving computer actually knows to separate them and map them back to what letters they were. Okay? So the problem here is that if there is an entity in between, okay, so this is Bob, this is Alice, and this is Eve. Even if the numbers are like this, even if a message says 97, 98, 99, Eve could easily understand the ASCII code because they could look it up on Google, right? And so they could know what each number represents as a letter. And that's problematic. You don't want that happening to your messages, right?
I do not.
So what do you do? The
do?
easy solution is you garble these numbers up, okay? And you garble them, you don't just add one. So if you add one, it's gonna be like 98, 99, 100, okay? You could do that, or you could do something smarter. You could say minus 10. So you could say 87, 88, 89, right? So you subtract 10 and your key is minus 10. You physically meet, okay, and give that key to Bob, who is gonna do plus 10. And they're gonna be able to like shift these numbers apart, go to the ASCII code again and understand it. But there's a little problem, okay? And you could probably see where this is going. Even if we physically meet and give us a good key, we could try all the different keys in the world. We could try +1, +2, +3, and we could try millions and millions of keys
Until we
and
find the right
review
one.
them, right? Until we get a message that makes sense, okay? And so if you remember in World War II, the Enigma machine,
The Enigma, yes.
yeah, one of the most complex machines ever. Do you know how it was cracked? It was a very bad mistake, okay? Because the people or the Germans used to say Heil Hitler at the beginning of every single communication. So they basically figured that Heil Hitler would equal a phrase of numbers. So it's like 07942. And if you know each letter represents what, it's not that hard, but you can actually figure out what the key is.
Then boom, they cracked the Enigma.
Yeah. Okay. One of the most complex machines ever, cracked by this way. So there's got to be a better way than a private key. It's got to be there. Okay. So this is where we move on to something called public key encryption. And it's the main idea here. And this is what you find when you go on to Google, when you go onto your browser. It's called the RSA algorithm, okay? It's one of the most interesting algorithms, really. So I'm going to tell you what it does. So basically, you have your message, ABC, you translate it to numbers, okay? And instead of just like adding a normal key, you do a really complex mathematical function to it.
Mhm.
The function is, it goes like this, okay? It says C equal M to the E mod N. Now, what are these very weird letters, okay? Let's handle them one by one, okay? So let's go on here from the right, okay? So in order for public key encryption to work, there's gotta be a number, a capital N, okay? And it's going to be a very huge number. That's a requirement. And it can't be any number. It has to be the product of two prime numbers. So what's a prime number? A prime number has its divisors as itself and 1. So you got 2, 3, 5, 7, 11, all these, 13, for example, all the numbers which you could divide by themselves are 1 only. Okay, so basically you'd have a letter N. Okay, and this is predetermined. So say this is Bob and this is Alice. Okay, Alice is going to be determining a number, a capital N, and she's going to determine two prime factors, P and Q. Now these are really secretive. You cannot share the P and Q. Next things next is M is easily just going to be the letter. Okay, it's the message. So you basically here you're gonna like handle each letter on its own. So you are gonna say M equals 97. Okay. And then, well, what is the E going to be? Okay. So let's clear up something. So the N is going to be publicly transmitted. It's not a secret. However, the P and the Q are a secret. Okay. Now, what else is going to be publicly known? Just two things: the N and the E. These are publicly transmitted by Alice to anyone who would hear. Now, what is E going to be? Okay. Well, we are going to have to calculate something else. Okay, it's called a phi or phi, and it's actually, its value is interesting. Its value is equal to P minus 1 multiplied by Q minus 1. Bear with me, Adam. I know this part is kind of confusing, but it's P minus 1 times Q minus 1. And then there is a bigger secret than P and Q, okay, and it is D. D is the key, and it's the secret key. If you know this, everything is overdone with. So D is only known to Alice because Bob is going to send, Bob is your browser, sending secret bank information, for example, okay, encrypting it with these two things, N and E, okay. Does Bob know the factors of N? No. P and Q are actually a secret with Alice. Okay? Sounds good?
Sounds
so
good.
How do we determine the E? Because that's a question we haven't answered yet. Well, E is called something, let me type here. It's called the multiplicative inverse of something. So that's really weird, but basically what you are going to try to do is you are going to say, you're going to bring a function called the GCD, and you're going to randomly try, okay, E and phi and phi, okay, until you get a 1. So you're going to randomly select E's until you get this phi with the GCD. You just plug in, and then you get your value of E. Okay, now what is the value of D here? So basically, I'm sorry, the D is the multiplicative inverse. So you're going to randomly select values as well with D, DE mod N, okay? And if you get that, okay,
Yes.
then that is your D. So how does this work pragmatically? Because we've just seen a bunch of theories here, okay? So let's try this example. Bob wants to send a message to Alice, okay? So Alice determined N to be a very big number, 19987, okay? And it determined E to be some other number, 78460. Now, Bob wants to encrypt a message of ABC. He's going to decrypt it using a very common formula called C equals M to the E mod N. So A is equal to 97, right? B is equal to 98, C is equal to 99. So C will equal to 97 to the power of E, which is given, over the public broadcast, right? And then mod N, mod is the modulus, so it brings the remainder. So basically you could just ignore that part because it's very common and it's very probable that you're gonna get the same result. So C is equal to this garbled garbage that no one knows. But that's just one letter, okay, that's the A. It has been translated, goofed up to an enormous number. But we gotta encrypt the B, right? Gotta encrypt the C. Gotta encrypt every single part of your message, okay? Now, once that is done, you need to bring these letters back. How do we bring them back? Well, don't worry. There is a way to bring these things back. It's called M equals C to the D mod N. Now that is beautiful because C equals M to the E mod N. That is the ciphertext or the encrypted text. In order to bring the message back, you'd have to raise that back to the power of D. Okay, so M equals, you could move out that C and write M to the E mod N, right? And raise that to the power of D mod N, right? Simple plugging, right? So what you could do is you could ignore that. You can say M equals M to the E to the power of D. So because mod N, because of something complicated, what will happen here is these will cancel out and you'll have M equal to M, okay? And that's the beauty of it all. It may not be very clear, but basically what I can promise you is this algorithm works, okay? So promise me that you'll be using this, okay?
I promise you that I'll be using this algorithm to send all my secret messages now.
Yeah, that's a great thing, because when you send a message as Bob and you send it back to Alice, okay, say ABC, it's gonna go here. Something that is very weird, that even your worst enemies don't understand. But Alice is able to understand it. Now, how can this go wrong? Okay, so that's a good question. How could all of this go wrong horribly? Okay, so we know that Alice transmits two letters, capital N and small e. Okay, now why does it go wrong? Why does it hurt to know the factors or the prime factors of N? Let me show you why. So the secret, the biggest secret ever is D, okay? So if I was able to, using a supercomputer, because this is even hard for computers to do, by the way, Okay, so if you bring a supercomputer and tell it what are the factors of capital N, the biggest computer you ever, it's not going to know. Okay,
Damn.
so if you were somehow able to figure out the factors, so you say N is like 10, and you were able to figure out that P is equal to 2, right? And Q is equal to 5. These two prime numbers make up that N. What you could do then is you could say, oh, that makes sense. Therefore, the phi, you could calculate that as basically 4. Now, why does that hurt? Because remember that d e mod phi equals 1 is the way you could get the d. So if you know the e, which you do because it's on public frequency, you were able to figure out the phi, okay, because you know the p and q, then you're easily able to figure out the super holy private key d. Okay, and so you just steal that and you'd be like, oh, m equals c to the d mod n. And c is all, you already have access over the encrypted stuff. You just raise it to the d and you're done. Okay, and so that's why there is concerns over quantum computing. Okay, because in the future, quantum computers could be able to figure out very large numbers and could figure out what their prime factors are. Now, if that
would be
happens,
so problematic.
very problematic. We'd have to look into something else, because now what all we're left with is really like, there isn't. I think we will reach a point in time where all of the world's privacy is unprotected. It may be possible that the United States government knows this, that it may be possible they have a way of cracking out these large numbers and they haven't told us, right? That is concerning. All of the world's communications right under their eyes. So I hope that you're going to use this public key encryption, and it's actually possible to do this in Python, but we're not going to go through that. But what I was willing to show you, okay, if you have time, Adam, tell me if you don't, is a very general proof on why this algorithm works. Care to see it?
I would love to see it.
Okay, that's